a topic that might be very important when you will do your master thesis. It's how to benchmark optimization algorithms. So in this problem, you have a set of different algorithms or approaches to solve an optimization problem. And you also have a set of benchmarks instances that are supposed to be representative of an unknown future set of instances that you want to use for your algorithm. The question is, how do you compare those algorithms in a fair way to make sure that you will select the best algorithms? The first solution that you might use is create a table like this one. So you have for each line the different types of benchmarks, and you have three different algorithms. We have algorithms R, M, and Z. And what you will measure is the performance. So for instance, it might be the quality of the objective function that you are able to reach after a given amount of time. And what we decide is that we will normalize the results according to the algorithms R. So for each line, we will say that this one should be equal to 1. And so we will divide every value by 417. So this one divided by 417, you've got this. This one divided by 417, you've got this. So the smaller, the better, of course. And you will do that for each lines, right? And then you will simply take the arithmetic mean of the ratio that you have computed. So clearly you will have 1 here for this algorithm R. And if this one, for instance, is a little bit larger, you will probably conclude that this one is a little bit slower. It's a little bit slower than this one. And so here you have even a larger value. So you will say that this one is the slowest algorithms, for instance. Okay, and so you might conclude based on this that this one is the winner and that you would like to prefer to select algorithm R for this set of benchmarks and for the unknown instances that you didn't see. Okay, but one choice was quite arbitrary here, is that we decided to normalize according to this column. What if you would normalize according to this column, no, or this column? So let's do it. We will normalize according to column M. And what we observe is that the conclusion is completely different. Now we will say that this one is the winner, this one is the slowest one. And in the previous slide, you see that we conclude that it was the best one. And now this one is the slowest one. Okay? So this is if we normalize according to algorithm M. And we reach a different types of conclusions. So what is the problem here? The problem is that the arithmetic mean that we use for normalizing the results gives meaningless results. So what we did here is that we computed here to reach that one arithmetic mean. And this was not a good idea to use arithmetic mean for normalized results. What should be used instead is geometric mean. If you use a geometric mean, whatever the column you choose for the normalization, you will come with the same winner. Okay? And so the only correct way to aggregate normalized results is to use the geometric mean. So be very careful if you take the arithmetic mean on normalized results. You might reach the wrong conclusion, and use instead geometric mean if you want to do that. And one paper explained that very well. It's called How Not to Lie with Statistics, the correct way to summarize benchmark results. Okay, that's a very interesting paper where they explain that you should prefer geometric mean.